Have you ever just stopped and wondered what the world really looks like? I mean, on the most fundamental level possible. We're talking about the world of individual atoms, a place so unbelievably small it's kind of hard to even wrap your head around. Well, today, we're going to dive into the amazing technology that lets us not just see, but actually touch this invisible world. So yeah, how do you see something that's smaller than a wavelength of light itself?
It seems like such a logical question, right? If you want to see smaller things, just build a better, stronger magnifying glass. Simple. But as it turns out, nature has a very, very firm rule that gets in the way. It's like a physical wall that no traditional lens, no matter how perfect, can ever break through.
And yeah, that wall, it's made of light itself. To really get why, we need to talk about what happens when light tries to interact with things that are just ridiculously, incredibly small.
Okay, so this is a phenomenon called diffraction. The thing is, light acts like a wave, and when those waves have to squeeze through a tiny opening, like say a microscope lens, they naturally spread out and get a little bit blurry. Now, if you have two objects that are way too close together, their blurry light waves just overlap and mush together into one single blob. And at that point, you've lost them. There's no way to tell that there were ever two things there.
This whole idea has a name. It's called the Rayleigh criterion. And you can think of it as the rule of the game for seeing things. It basically says, if you want to see smaller details, you absolutely have to use a wave with a smaller wavelength. The smaller the wavelength you use, the finer the detail you can resolve. That's the rule. And here is the big problem. An atom is about 0.1 nanometers across. The wavelength of the light we can see? It's between 400 and 700 nanometers. That's hundreds of times bigger. It's like trying to feel the shape of a single grain of sand while you're wearing giant boxing gloves. It's just not going to happen. It is physically impossible. We've slammed right into a wall.
So, if light is out, if it's too clumsy to do the job, what can we use? Well, this is where human ingenuity gets really, really clever. Scientists came up with one of the most powerful tools we have for looking into the unknown, the transmission electron microscope, or the TEM.
The brilliant, game-changing idea was to just stop using light altogether. Instead of using photons, the particles of light, they decided to use electrons. And thanks to the wonderfully weird rules of quantum mechanics, we know that particles, like our friend the electron, can also behave like waves. So you can think of a TEM as a super-powered, souped-up version of the optical microscopes you might have used in school. But instead of glass lenses bending beams of light, a TEM uses powerful magnetic fields as lenses to aim and focus a beam of electrons. And here's the kicker. These electrons can have a wavelength that is way, way shorter than visible light.
Okay, so here's how it works, in a nutshell. First, an electron gun shoots out a stream of electrons. Then, a massive voltage, we're talking hundreds of thousands of volts, slams into them, accelerating them to insane speeds. These magnetic lenses then focus that high-speed beam onto a ridiculously thin slice of whatever you want to look at. As the electrons blast through the sample, they cast a kind of shadow, and that shadow creates a 2D image on a screen at the bottom.
Now this right here, this is the secret sauce. It all comes down to a fundamental idea from quantum physics called the de Broglie wavelength. It says that the faster you make a particle move, the smaller its wavelength gets. So by zapping these electrons with a huge voltage, we get them moving at a pretty good fraction of the speed of light. And that incredible speed shrinks their quantum wavelength down to something unimaginably tiny.
And this is the whole breakthrough, because we now have this incredibly short electron wavelength. We can go back to that old Rayleigh criterion, and the game is totally changed. A modern TEM can resolve details down to 0.1 nanometers. That's the perfect scale to see the beautiful, ordered arrangement of individual atoms inside a material. We finally did it. We smashed right through the wall of light. But what if you don't really care about seeing through a sample? What if what you really want to do is map its surface, atom by individual atom? For that, we need an even more exotic and frankly kind of mind-bending tool, the Scanning Tunneling Microscope, or STM.
Just look at this for a second. This is not a computer model. These are actual individual gold atoms just sitting there on a surface. And the STM doesn't see them with waves at all. It's more like it feels them. It traces the atomic landscape, kind of like a blind person reading Braille or a needle running over the grooves in a record.
So how does it do that?
Well, it uses one of the absolute weirdest effects in all of physics: quantum tunneling. So the STM has this incredibly sharp metal probe. And when I say sharp, I mean the tip is literally a single atom wide. You bring that tip extremely close to a surface that can conduct electricity. You apply a little voltage, and something amazing happens. Electrons can suddenly just jump or tunnel across the empty gap. This creates a tiny but totally measurable electric current.
Now, the secret is that this tunneling current is ridiculously sensitive to distance. If that probe tip gets just a tiny bit closer to an atom on the surface, the current shoots way up. If it moves a tiny bit away, the current just disappears. So the microscope uses this trick in one of two ways. It can scan at a fixed height and just measure how the current changes. That's fast, but it only works for super flat surfaces. Or it can move the tip up and down, keeping the current perfectly steady. That's slower, but you get a stunningly precise map of the atomic bumps and valleys.
All right, so we've got two unbelievably powerful ways to see the nano world. Let's put them head to head. A little microscope showdown, just to really get a handle on when you'd use one versus the other.
Okay, let's break it down. The TEM, that's for looking inside things. It shoots electrons through your sample to give you a 2D projection of its internal structure, but you have to slice your sample paper thin. The STM, on the other hand, is all about the surface. It maps the bumps and dips on the outside, but your sample has to conduct electricity. But if you look at that last row, you can see the STM has a secret weapon, a special power that goes way beyond just looking at things.
And this is where science fiction really starts to become science fact, because the STM isn't just a microscope, it's also a pair of atomic-sized tweezers.
That's right. The quantum interaction between that probe tip and an atom on the surface is so precise that scientists figured out how to use the STM to gently pick up a single atom and move it somewhere else, placing it exactly where they want it. This isn't just looking anymore. This is building. This is construction, one atom at a time. And if you want the ultimate proof, the ultimate mic drop moment for this technology, look no further than this. Back in 2013, scientists at IBM used an STM to make the world's smallest stop-motion movie. Every single dot in this little stick figure is an individual carbon monoxide molecule that they painstakingly dragged into place, took a picture, and then moved again for the next frame. It is an absolutely mind-boggling feat of engineering on the smallest scale imaginable.
So think about that journey. We went from being blocked by the physical limits of light to using electrons to see inside things, to literally feeling the contours of a single atom. And now, we're building tiny structures, molecule by molecule. We've gone from being totally blind to the nanoworld to becoming architects within it. And that just leaves us with one final fascinating thought. Now that the toolbox is open and we can see the atoms and move them around, what incredible things are we going to build next?